Continuing in section 3.4, we're going to graph a linear inequality, and this time the boundary goes through the origin. Our linear inequality is y minus 3x is less than 0. So to begin, we want to determine if our boundary line is dotted or dashed or solid. Because the inequality contains a less than and not a less than or equal to, we can say that this is a dashed or dotted boundary. So all the points on that line that lie on the line are not solutions, but that line is a boundary between all the points that are solutions to the inequality and all the points that are not solutions to the inequality. So our boundary, just keep in mind that our boundary is going to be a dashed line. So let's look at our boundary equation. Would be y minus 3x equals 0. This equation we can write in slope-intercept form by adding 3x to both sides. We get the boundary equation is y equals 3x. So we can also think of this as 3x plus 0, so we can identify the slope of the line is 3. We can write it as 3 over 1, and the y-intercept of the line is 0. So begin by plotting a point on the origin, which is your y-intercept, and moving 3 units up and 1 unit to right, and that's another point. We're going to draw a dashed line through those 2 points. So that line is a boundary between all the points that are solutions to the inequality and all the points that are not solutions to the inequality. To determine which side, either all the points above or all the points below, we need to pick a test point, a point where we can determine if the inequality is true or false. You have many test points to choose from. So let's begin by testing a point, say over here, where let's say right here is my test point when x is equal to 4, y is equal to 1. So I'm testing the point 4, comma 1 in my inequality. And always go back to the original inequality here. Well, where my inequality is y minus 3x is less than 0. I'm going to put my test point x and y value into the inequality, and the y I chose was 1. Is 1 minus 3 times our x value. Is that less than 0? Well, if we simplify, we have 1 minus 12, and 1 minus 12 is negative 11. Is negative 11 less than 0? In this case, it is true. So it does satisfy the inequality, and it is a solution to the inequality. So all of the other points that are on the same side of this line are also solutions to the inequality. So there's an infinite number of solutions. And because we found our test point at 4, 1 was true, all the other points on the same side of that line would also be true. If you chose a point somewhere on the other side of the line and tested it, that should be false. For example, if we chose a point, say, right at negative 2, 4, that's our test point. To test that, we are going to, we're going to test the point I selected was x is negative 2 and y is equal to 4. I'm going to plug that into my original inequality, replacing y with 4 minus 3 times our x that I selected was negative 2. And by simplifying this, I get 4 minus 3 times negative 2. Distribute that negative and you get 4 plus 6. And 4 plus 6 is equal to 10. Is that less than 0? Okay, this would be false. So it is not a solution to the inequality, and none of the other points that are on the same side of that dotted line, that dotted boundary line, are solutions to the inequality. So the solution to the inequality is a collection of all of those points that are in the shaded region up until you get to the boundary line, but the points that are on the boundary line are not solutions. All right, in this example, we are graphing the intersection of two inequalities. We want to find the solution of 3x plus 4y is greater than or equal to 12 and y is greater than 2. What we do is we can graph each of these two inequalities separately, and then we want to find all of the points that would fall into the shaded regions of both. And then we would put those on a graph by itself that denotes the intersection of those. Our first equation that we'll graph is 3x plus 4y is greater than or equal to 12. I'm going to take that equation and I'm going to write it as equals 12 for my boundary, and you should also note that this line is going to be a solid line because a solid boundary line because we have that greater than or equal to. And this inequality, y is greater than 2, is going to be a dashed or dotted line because the inequality is a greater than sign. It doesn't have the equal bar underneath. So let's graph the boundary line, and to do this we're going to solve for y so we can get the equation in the form of y equals mx plus b. I'm subtracting 3x from both sides, and I get the equation 4y is equal to negative 3x plus 12. Then I'm dividing both sides of the equation by 4. And I get the equation y is equal to negative 3/4 x plus 3. I'm going to plot my 2 points. I'm going to use yellow here. The intercept is positive 3, and the slope of this line is negative 3/4. So that's a rise of negative 3 and a run of positive 4. I'm going to draw a solid line through those that indicates the boundary of the inequality. Now I need to decide which side of the line contains a solution to that inequality by picking a test point. The test point that I'm going to pick is the origin. If the inequality is true when I test the origin, I would shade that side of the line. If it's false, I'm going to shade the other side of the line. So I'm going to test the origin 0, 0 in the original inequality where 3x, I'm going to replace x with 0 plus 4y, replace y with 0. Is that greater than or equal to 12? By simplifying, I see that 0 is greater than or equal to 12 is false. So that is not a solution to the inequality. So anything on that below that line would not be a solution to the inequality. Everything on the other side. So I would shade everything above that line. All right, now let's look at the next equation. Y is greater than 2. Remember, this equation only has a y in it, so that should indicate it's a special type of line. Think of hoy, right? H-O-Y. It's a horizontal line, the slope is 0, and the equation of the line is in terms of y equals a number. So this is going to be a dotted line or dashed line that goes through positive 2 on the y-axis. Let's graph the dotted line. Now I need to test to determine whether to shade above this line or below this line. And the test point that I'm going to choose is the origin. You're going to plug 0 into the inequality and test to see if the inequality is true. So I'm kind of putting it all together up here. Test the point 0, 0 in the original inequality. The y is 0. Is 0 greater than 2? Well, that's another false. 0 is not greater than 2, so the origin is not a solution to the system of equations, linear inequalities. So let's shade the other half of the line, the above the line. All of the points in this shaded region are solutions to the inequality y is greater than 2. Now we're going to put these both together on the third graph and only shade the part that would overlap. So I have my two boundary lines. Notice that the first equation is a solid boundary and the second equation is a dotted boundary. If you were to overlap these two shaded regions, the part that would be overlapped in both sections, if you're using a highlighter and using a yellow highlighter for the first one and a blue highlighter for the second one, then and putting them on the same graph, you'll see the part that overlaps is going to turn green. So the overlapping part would be this region here. And that would be the solution to both inequalities. You have the whole yellow section here from the first, the blue shaded region here from the second, and then that part that overlaps is the only part we're looking for. So when you're graphing your solution on my math lab, you would use that bucket tool and only pour the shaded part into that region that's green. That's the solution to the system of linear inequalities.